Okay, so welcome everybody to the next Heidelberg Joint Astronomical Colloquium. And this week we're going into the center of the galaxy, and we have an absolute top person worldwide to tell us all about that. This is Rainer Schoedel, and I'll hand over to Matthias Solmani to make the formal introduction.
Thank you. So it is an honor for me to introduce the speaker of today, Rainer. So Rainer obtained his PhD at the Ludwig Maximilian University at the Max Planck Institute for Extraterrestrial Physics in Munich in 2004, where he was directly involved with the groundbreaking work about the stars orbiting the central black hole of the Milky Way that led to the Nobel Prize 2020 to Reinhard Genzel. After his PhD, Rainer spent 5 years as a postdoc in the group of Andreas Eckert in Cologne. And in 2008, he moved to Spain with a Ramon y Cajal fellowship at the Instituto de Astrofísica de Andalucía, where he has been ever since and is now a tenured staff and leader of the Galactic Center group. So Rainer is widely known for his studies on the structure, stellar population, and formation history of the nuclear star cluster and nuclear stellar disk, and he's the PI of the Galactic Nucleus Survey of the center of the Milky Way, and has coordinated several other international campaigns to observe the Galactic Center. And in 2014, he also obtained an ERC consolidator grant. So, without further ado, I look forward to your talk today and to learn more about the Galactic Center.
Okay, thank you very much, Mattia. Thank you, Richard. Thank you very much for the invitation. Football is better because usually you talk the expectations down of your team, but in science you get introduced and, oh, there's this great thing and that great thing, and so it's dangerous, I think, too high the stakes. But I'll try to do my best. I'm really happy to be here. I really love coming to Heidelberg, I have to say. And this time it's a unique experience because usually I'm at Max Planck up there and I'm down in the valley, and I don't know, there's just a gazillion of little secret safe houses for astronomers throughout the city, and it's very impressive. I really enjoy my time here scientifically and also privately always. Actually, we were just talking, and I thought I was just here just a few years ago at the Joint Astronomical Colloquium, but I just dug this out, so this was in 2010. Of course, time evolves faster as we get older, but also, I mean, a few years we just lost them to the pandemic. I think we all have kind of a gap in our brains there. So that was continually evolving, our understanding of the Galactic Center. It was 10 years ago. And again, I show you this kind of a relatively generic title, but I'll write you through a lot of different aspects of the Galactic Center and show you what an exciting target it is, what a unique laboratory, and all the things that can be done there. I will not be able to touch on all interesting aspects. I will be omitting many things, but I don't want to keep you here longer than 45 to 50 minutes. So, at the start, I always like to define a bit what a galactic nucleus is for me in my talk. So I basically concentrate on the mass, what's there as the mass, and what's in there in galactic nuclei. Well, first of all, this is black holes, of course. This is something I copied from a talk. I think I copied it from Nadine Neumayer several years ago. This figure, it's kind of self-made now, but the inspiration is from Nadine. So this is really, so first thing we think of galactic nuclei is of massive black holes. Of course, they're very popular, they're prominent. We've all heard about them already during our studies. And of course, the bigger the bulge, the spherical component in the galaxy, the bigger the black hole. So we have these things. Our Milky Way, somewhere around here, it's actually kind of a underperforming black hole. The second thing, slightly less well known, although also now diffusing through the general astronomical communities, nuclear star clusters. These are these really compact globular cluster size objects that reside at the centers of many, many galaxies. They appear here as kind of fuzzy balls in these Hubble Space Telescope images, but this is at several megaparsecs distance. They have masses that are several times globular clusters, and they're really the most massive and densest stellar systems that we can observe in the universe, in the local universe at least. Interesting thing is, nuclear clusters are more frequent even than the massive black holes, as far as we know currently, or at least as frequent, because they're everywhere. So this is also from a review from Neumeier, Seth, and Böker. So you have, this is the stellar mass of a galaxy, so the Milky Way is here at 10 to the 11. And this is early and late type galaxies. And we see, okay, when they're very small, it's not quite sure. Maybe there's also some biases and so, but at 10 to the 8, basically all of them have these nuclear star clusters. And they stay there in the spiral galaxies, and then in the really giant ellipticals, they disappear, which is most probably because these are merger products. In the end, you have to merge 2 or 3 or more massive stellar black holes, and of course you have to get rid of the angular momentum and eject stars, and that destroys anything that is in there. So I've already said these things are massive. They are very frequent. They are basically everywhere. A few parsecs effective radius. We know that they also coexist with massive black holes, like in our own Milky Way. I'll come to that. They are very interesting because they show scaling relationships with the host galaxies. They may even be the places where galactic black holes form via runaway collisions. They're, of course, prominent source regions for gravitational waves. You can merge stellar black holes in these things without ejecting them because they have a very deep gravitational potential. So it's clearly that it's obvious that we want to understand and study these things. I would say that the nuclear star clusters are at least as exciting as the galactic black holes. Now, there should be a number 3 here. Let's go to bigger scale still, and still less known, because only now getting it more attention, is nuclear stellar disks, or maybe inner bars or rings. These are larger. These are like, let's say, scales of 100 parsecs where we are now. And actually these structures are very common in barred spirals, very frequent, as has just been shown with a survey with the new MUSE instrument, Gadotti et al. And they also tell us something about, of course, galactic history. They need to be fed with gas to form the stars. They get destroyed when you have mergers, for example, and created by gas inflow. Okay, these are basically 3 components the large-scale components we know at the Galactic Center, and now we'll turn our attention towards our own Milky Way, where we have everything close up. So this is one of these nice illustrations that came out from Spitzer, actually. Spitzer survey, so it's a current model of the Milky Way, although arms appear and disappear with a certain frequency of a few years. That is never quite clear how many arms and where exactly they are. But I think it's slowly converging. So it's continually evolving, in fact. So from the vantage point of the sun, if you look towards the galactic center, it looks like this. In the infrared at 4.5 microns. Of course, if we want to look all the way through the galactic plane, we definitely have to go through the infrared. We cannot do this in the optical. And actually from these kind of images, it became apparent from these images and then from radio astronomy and gas dynamics that there must be a barred potential at the center of the Milky Way. Here you see it basically because it's asymmetric. The bulge, or what appears to be the bulge when you look at in projection, is thicker on one side than on the other side. This indicates that it's actually a bar. We're looking along a bar, and it's not at all clear whether we have anything like a spheroidal bulge in the Milky Way. Maybe we have. There's probably some indication of something, but it would not be more like 10% of the mass of the actual bar. So the galactic center, all of this that I've talked about, fits into this small black dot. So it's really a tiny area of the entire galaxy, but it's probably its most exciting part. This is the same thing in projection, roughly, when you look at the nuclear stellar disk, nuclear stellar star cluster, and black hole in the projection, it would occupy this size. So the structures that we have, this is, you have this nuclear stellar disk and the nuclear cluster and black hole at the very heart. And if you want to see what happens in the optical, this is the optical view of all of this. So you see we cannot study anything. And this makes our life very hard, by the way, because, for example, if you work with filters, with photometry, in the visual regime, it's relatively easy to identify what kind of star you're looking at. In the infrared, it's almost impossible. So this is an overview now from a Spitzer image. This is kind of scaled down, so I smoothed this image so you see the main structures. This would be the nuclear stellar disk. By the way, I always use the term nuclear stellar disk. It's not 100% certain that this is actually a disk. There could be a slightly more ring-like structure, it could be an inner bar. I mean, a disk is a very plausible model, so, but I use it. I mean, no one so far has really actually proven it's a disk, but it's a model that works very nicely and is very plausible. So this has something like 1 billion solar masses. We have the nuclear star cluster in here, and of course, then such a star at the very heart of it. So we have the advantage compared to like the Andromeda galaxy that everything is nicely centered on each other. In an actual image, it looks like this. So this is a mid-infrared image from the Spitzer Space Telescope that you always see when you have a Galactic Center talk. You always will see this Spitzer image. And just to get an idea, on the sky, it looks like this. So this is the full moon on the sky in comparison. You clearly see, so now let's see why we have such a unique laboratory. I will be going on how great the Galactic Center is all the time here. Well, it's just the center of I don't know how many hundreds of billions of galaxies in the universe. But yeah, it's just a question of proximity. That's the only thing that's really cool about the Galactic Center is that it's really close. This is why it's so cool. So this is a view of the Andromeda galaxy, and on exactly the same angular size, this is what we get on the Milky Way. So this is 150 light years here, and this is 100 times better. So of course we can do stuff in the center of the Milky Way. It will always be better than the rest of the galaxies because it's just 100 times closer than the next comparable nucleus, 1,000 times closer than the next AGN, and this is just, it's a unique laboratory. It's like the solar system is the only laboratory that we really have for studying planets up close, and this is what the Milky Way is to us here. So let's, so this is just this size scale here. Let's go on then. So we will now step from the very inside out. Let's start with the black hole. I will not talk too much about the black hole because I'm sure all of you have heard a lot of it, about it in the last few years. It's a very famous black hole. So recently, of course, we've just had the Event Horizon telescope showing the image. So let's go back again to this Spitzer image. Now here we see the nuclear star cluster. It really is very nicely visible on this image. And it's really a separate entity, as you can see. Now let's move in. This is now with the VLT instrument at the diffraction limit of an 8-meter telescope, seeing basically a region of 2 by 2 parsecs. Here you already can easily identify 20,000 stars in this image. We want to zoom in further. This is now, again, a false color image of the central parsec. And the black hole really resides inside here. So we are now at an angular scale. This is just 1.5 by 1.5 arc seconds. So for many of those of you who do not do diffraction limited imaging at major telescopes, this is usually the size of a star, what you here see. Or maybe you can just resolve 2 stars and this. And here you see several dozens of stars already. In this is also this adaptive optics, it's also heavily treated. So we see we have this very dense cluster of objects. We have actually such a star as a variable source here. I'm not going to talk about the variability. Just to say, such a star is really dark, and there's very good arguments that you need an event horizon in order to hide, even though it's accreting very, very little mass, but you need an event horizon. So it's very, very faint, but sometimes you see it. Sometimes there's like space weather around such a star, there's magnetic reconnection, particle acceleration, and it's highly variable. This is the most famous, one of the most famous stars in the galaxy. This is S2 or SO2. This is the star that does the 16-year orbit and the first star for which an orbit was detected on such a star. And this is my lucky star because I used to be at the right place at the right time. I was doing my PhD thesis there, so that was like, yeah, the gift of the cosmos to me. Then there's some other star here, fainter star that has another 20-year time scale. But you see, it's not, these things are not awfully faint. This is 17th magnitude in K-band and at 2 microns in the near-infrared. This is not awfully faint. It's just so difficult to see these things because it's awfully crowded in there. And yes, and then I don't know whether you see this nicely. You can actually overlay the orbit. So this is the orbit of S2. This is another orbit of this. Okay, this is depending on where you, on which side of the ocean you live, you have different numbers for these stars. But the most important thing is the things that with the little numbers, they basically have very short orbits, orbital timescales below 20 years. So you can do nice experiments in the human lifetime. This is another view of other orbits. So this is one of the numbers. This is older numbers from 2016 from orbits. 4 million solar mass, 7.9 kiloparsec distance. And now, for example, if we cross the ocean now and go to Reinhardt's group from Max Planck Institute for Extraterrestrial Physics, Reinhard Gentzler and Frank Eisenhower, and they have this incredible gravity interferometric instrument at the VLT working now and do hyper-precision measurements. And now you see how perfect this orbit looks here. I have not put in the result of the Schwarzschild precession, but this is just a Kepler orbit, which is perfectly fitting. This is the second passage around the black hole of this star, and now you have really measurements to the percent level, few percent level of the mass of this black hole and of its distance. This is fantastic because this is really precision astronomy. My first astronomy lecture, I remember, I think it was Ralph Bender who insisted on the fundamental law of astronomy, and that is, does anyone know the fundamental law of astronomy, by the way? What is really fundamental in astronomy? Not so much talking to theoreticians, more the observer. Fundamental law is 2 equals 1. But here this is not true anymore, the fundamental law. This is really precision measurements now. Another one, so I remember Andreas Eckert at Cologne University, he used to say, the error is always 30%. Just estimate the error. When I was, how do I do the error? How do I calculate the uncertainties here? And he said, it's always 30%. I said, that's not true. So I spent 2 months figuring out the uncertainty of something that I did, and it turned out 30%. And then, of course, Andreas said, look, I told you already. Why did you do this? But yeah, actually, this is the proof that it's actually worth to invest heavy efforts into precision astrometry. And they recently just showed Schwarzschild precession, so this is a very, very nice work. Okay, so far to the black hole. I'll come back to the black hole at the very end of my talk. I'll philosophize a bit and try to make a fool out of myself thinking about when and how such a star acquired its mass. So let's go to the nuclear star cluster. This is where I went basically when I finished my PhD. I tried to zoom out a bit. And actually nuclear star clusters were, even at the beginning of the 2000s, just an area that is now, that was emerging. So you have Nadine here in Heidelberg, and of course the entire Galactic Nuclei Group does heavy work on these nuclear clusters. So you are all familiar with it, but it wasn't so much 20 years ago. And there was one meeting once in Leiden where there was also the question, what in the center of the galaxy, what's going on? And then this motivated me to use the Spitzer images to work on this. So you see, for example, already one problem, even at 2 microns, which for extragalactic people, 2 microns is already the very deep infrared. For us at 2 microns, we have still huge problems with interstellar extinction. I mean, visual extinction is 30 magnitudes, but it's still like 2 to 3 magnitudes here, and there's lots of infrared, even mid-infrared dark clouds in the Galactic Center. But it gets better once you get to 4.5 microns. There you're really in an optimal window. So this is also why James Webb Space Telescope will be just fundamental. For example, if you want to observe edge-on galaxies and all this stuff, you just have to go to the mid-infrared. So you see, of course, there's this nuclear cluster, but it's still difficult to get its structure. So what one can do is you get rid of all the bright stars, you smooth it down a bit, you try to correct for extinction, and then even nicer, you just say, okay, the thing is going to be probably symmetrical along the galactic plane and its rotation axis, and then you can symmetrize it and it looks like this. There's good arguments to do this. And yeah, you find that this thing is really centered precisely on such a star. The stellar density peaks exactly on such a star. In the 90s, actually, the light density does not peak on the black hole because there's a dozen very supermassive, extremely massive young stars around, and the light density is offset from ZJ star, but the mass and the number density peaks on ZJ star, the dynamics peaks on the kinematics on ZJ star. It's really perfect. This thing is slightly squashed together, so it rotates along with the galactic rotation, so it's slightly flattened. Half-light radius, roughly 4 parsecs, so this is like in a nice globular clusters, but a lot of mass. 25 million solar masses, roughly, give or take 500,000 mass or 1 million mass, but this is really, really a massive dense thing. If you look at kinematics, this is work from Anja Feldmayer. So here you see the rotation. Blue is coming towards you, red is going away, and this is basically, if you look at it, the front part is moving eastwards and westwards, the back part. And in the central 2 parsecs, you're mostly pressure supported. There the random motions are more important than the rotation. And then if you go further away, you still see this. So this is really exactly galactic rotation. So there you already can see that this must have formed somehow from stuff that has been falling in somehow along the galactic rotation axis. Now the star formation history. Okay, here I'm viciously, I should have prepared it. I'm viciously ignoring other people's work here, which is bad. So I'm just showing what I did with my group here. I hope I mentioned that. So there's old, there's work from Blum et al. 2003. There's important work by Oliver Poole from MPE, from spectroscopy. And what I did here was doing very deep, just imaging. And then we derived the luminosity function for the stars. As you remember, we cannot really say anything about what the stars are in the infrared, because most of it is just Rayleigh Jeans bodies. And most of it is giants. But we get this luminosity function. So here you have the magnitude, you have the number, it's logarithmic. It's roughly exponential, and you have a few bumps in here. Then I separate, so blue and red is just separating inside 0.5 parsecs and outside 0.5 parsec radius from the black hole, and this is just shown here. It's just very much the same. So it's kind of nicely mixed, at least on this scale of the inner parsec. So the black line is the interesting thing, and there's a few things in here that you can learn about the evolution. So this is well mixed. Then here in this region you have the so-called asymptotic giant branch bump. This thing here is the red clump bump. This is kind of the giant main sequence where you have helium shell burning in the giants, in low mass giants, 1 to 2 solar masses, and they stay there for a long time and accumulate. Actually, this would be a far bigger dip if there were no young massive stars. So young massive stars appear here, and then at the faintest part here where we in the end then run into incompleteness issues because of crowding, this is where the main sequence is. So then you can use model luminosity functions and fit it to this. And this is a slightly more complicated diagram now. But this is basically, these histograms are just histograms from Monte Carlo simulations of fitting star formation histories to this. And what we find is that the mass, prominently 80% of the mass fraction formed very early on. So this is like 11, so it's basically roughly 10 gigayears and older. 80% of this nuclear star cluster. Then we have here an event that was roughly 3 gigayears ago, where we have formed something like 15% of the nuclear star cluster. In between, not much happened. This is this yellow histogram, maybe a few percent, maybe nothing. And then it picked up again recently, so in the a few hundred million years ago, a few percent, and in the last 100 million years, 1% or so of the mass. So this thing is old, it's the first message. We see a clear minimum in the star formation 1 billion years ago. That has been also seen in the spectroscopic observations by Oliver Poole or by Blum et al. The thing is, if you have a 1 billion-year-old star formation event, the red clump stars actually do not. Red clump stars are kind of a standard candle, but not when they're 1 billion years old. These 1 billion-year-old relatively massive red clump stars are actually fainter, so you would see a clear double red clump, as we see in the nuclear stellar disk. I'll come to that. So there was this 3 gigayear event, and a few percent of the mass in the last few hundred million years. Also interesting, So the mean metallicity, and this is not just my work, there's also Matthias Schultheis, for example, from Nice Observatory. So the mean metallicity gets high in this thing. So we're above twice solar metallicity in there. So this is another thing. So 30 years ago, people would say, yeah, Galactic Center, it's bulges, it's old, it's not particularly metal rich. No, this is really metal rich. It's probably it's the most metal rich zone of the Milky Way, full stop. Another thing that's quite interesting, if you have a dense stellar cluster around a massive black hole, all stellar kinematics people, all theoreticians will tell you, whatever you do, whatever method you do, you will always end up forming a cusp around the black hole. That means the stars will show kind of an exponential increase in density around the black hole. It's so-called the Barkholt-Wolff cusp. We see something like that. This is a bit of a thorny issue. This is just 0.2 parsec around the black hole. So if you go to the faintest stars that we can reasonably observe and count, you see this exponential increase. It is slightly flatter than the theoretical predictions, but okay, that can have many reasons and biases. But yes, there is this cusp in the faint stars, kind of a bit fainter than red clump, and then the subgiants. However, if you go to here this 14th magnitude or brighter, the real bright giants, they are deficient. That has been known since the 1990s. The new thing is that now, since a few years, we really know that the fainter stars, yes, they do show what we expect from theoretical stellar dynamics, but the very bright, big giants, something has happened to them. Not going into that, that's one of the many interesting topics that there's not enough time in such a review talk to touch, but there can be many reasons. It can be collisions with star-forming clumps. It can have been past jet activity from such a star. It may also be collisions between stars and stellar remnants. There's a broad zoology of models out there, and all of them may play a role. Why in the innermost, in the densest parts? I mean, it kind of makes sense. You're in a very dense part, lots of stellar density. When gas is in there, it's dense. The orbital timescales are a few hundred, a few thousand years at most. If you have a big fluffy thing around there, maybe you can remove its envelope. So I finished this overview of the nuclear star cluster with a nice schematic that Tal Alexander, the late Tal Alexander, who unfortunately left us in 2018, I think, or 2017. He made this great schematic of the nuclear star cluster. It's not fully to scale, but it has all the important things. So let's go from the outside in. The influence radius of the black hole is roughly 2 parsecs. As you've seen, the nuclear star cluster mass is about 8 times bigger than the black hole's mass. So actually, if you go a bit away, gravitationally, the black hole is already not important anymore in the Milky Way. Quite interesting lesson, just 2 parsecs. And there you have all these old stars, red stars. Then you find a disk of young stars when you go further in. I have not mentioned them. There was a star formation event a few million years ago. I'm sure somebody from Max Planck, from the extraterrestrial physics, has talked about that. Another topic that I will not mention too much, the stars immediately surrounding the massive black hole are also pretty young massive stars, B dwarfs. They cannot have formed there. They may have gotten there because they form as binaries and then undergo a 3-body mechanism with a central black hole. One star gets ejected as a hypervelocity star and the other one is tightly bound, remains tightly bound. Maybe you have something like an intermediate mass black hole floating around. I'm not such a fan of that. And some younger clusters around there. You have molecular clumps in the so-called circumnuclear disk. And then on larger scales, you have giant molecular clouds and this other phenomena. I would add now to this also, we have now already strong observational evidence that there's also a cusp of stellar mass black holes. So we know that from X-ray observations and also from radio observations that the density, and this is fully in agreement with what you would expect, stellar mass black holes are kind of the long-lived heavy objects, so that by dynamical friction they will sink towards the center, and we see by X-ray an overdensity of them. So in the central parsec, there may be easily 20,000 stellar black holes. This is also exciting because, of course, what nowadays everybody wants gravitational waves. So this is what you get from these kind of targets. Let's go further out to the nuclear stellar disk. Here's a very nice image that was actually from a work about a potential hot X-ray plasma in the Galactic Center. This is from Shogo Nishiyama, an old collaborator of mine. And it's from their Galactic Center survey, Sirius IRSF survey. And this is stellar counts. And I love this image just because it shows very nicely the shape of this nuclear stellar disk. I've already mentioned it has a mass of roughly 1 billion solar masses. So Mattia here has done very detailed modeling of the gravitational potential. A half-light radius, 150 parsec, rather like 100 parsec. It's extremely flattened, so it's a very flat thing. Vertically, you have a scale height of 30 to 40 parsecs. So this is a lot flatter than the large-scale disk of the Milky Way. So this is really a flattish object there. You see it also this is from Apogee survey from Schönrich et al. Here you see the fingerprints of their fiber instrument and the velocities of the stars, and you see again this blue-red pattern. So it's a nicely rotating disk. It's a flat, cool, rotating disk. Not ultra cool, though, I would say. It's not that cool. I mean, right? Warm, yeah, it's warmish. So it really has some pressure support. So rotation velocity somewhere around 100, 120 kilometers per second. It really coincides with the so-called central molecular zone. It may have formed from gas in there. I'll come to that a bit later. And yeah, the vertical size, I would rather put this to 30 to 40 parsec. It's really flat. So let's look at the kinematics. We have already seen it's a rotating thing. Let's see what proper motion does us. So this is from Banafsheh Shahsamanian. She was postdoc with me until briefly ago. She did a proper motion survey of this. So let's first start this is the innermost maybe 30 by 80 parsecs, just a small fraction. I know the quality is not too big, so I'll show you. You see a histogram here. This is just n here, it's the number of stars. And this is the proper motion perpendicular to the galactic plane, okay? So we're in galactic coordinates. And this blue thing is a histogram. And yes, what do we need to fit this histogram? We actually fit it nicely with two Gaussians. Both are centered on 0, and one is relatively broad. There's this green line here. You probably cannot see it. I apologize. So it's a broad green line and a narrow one, a narrow histogram. One has 3.2 milliarcsecond per year, sigma, and the other 1.5. The thinner one is the nuclear stellar disk because it's cooler. You know, it's flattened. The thicker one is actually this coincides super nicely with measurements of the velocity dispersion of stars in the galactic bulge or inner bar. I don't like to use the word bulge with our galaxy because it's rather bar. So this is velocity dispersion of stars in the inner bar. Now what happens if you look now parallel to the galactic? So this is the bulge, this is the nuclear stellar disk. And now we're parallel. We see actually we could kind of fit this with two Gaussians, but we fitted it with three. Now, if you know Mike Rich, he always talks about the Martini rule. One Martini is nice, one Gaussian is nice, two Martinis is better, three is overdoing it. And so he always says, so caution when you have 3 or more Gaussians because you can fit a lot of Gaussians into anything. But I actually insisted on using 3 Gaussians because if we have this bulge Gaussian, we need it also in the disk. We need this bulge. It must be present also along the galactic plane. And when you force it, it's in there, and it has also a velocity dispersion, again, of 3 point something milliarcsecond per second. And then we have these slightly broader nuclear stellar disk Gaussians, which are in the front and at the back of the nuclear stellar disk, because again, we have a rotating structure. So this work is done by Banafsheh Shahsamanian. Unfortunately, as so many of us, she had to leave astronomy. Is doing data science now, but is happy. So if we look at this in a slightly different way, so here this axis here is motion along the galactic plane, and this is motion perpendicular to the galactic plane. It's just spinning it in a 2-dimensional histogram. And what you see, so H minus K, this is H and K are 2 near-infrared filters. H is shorter wavelength than K, so smaller number means bluer, bigger number means redder. And so here we have redder star on the right, this is bluer stars, and we see the blue stars move preferentially eastwards, and the redder stars westwards, and this is again because the redder stars are at the backside of the nuclear stellar disk and suffer more extinction, more reddening. So the formation history, this was very nice work by Paco Nogueras, who is here in the audience during the end of his PhD, actually. That was very, very nice. He realized there was a double red clump in our data, and that inspired then all this work here. And here, this is again, I don't go into the details. What we see is basically in very rough variable H bins. Sorry, let's first go this. And using two different stellar evolution models, FASTI and MIST, to make sure we don't fall into the trap of big systematics here. You see that again, a lot of it, up to 90%, is older than 8 billion years, at least within the field of view that we have examined. Then you have a gap. The MIST models have something with the big error bars. The FASTI models give us 0 between 1.5 to 8 billion years ago. This is a bit strange, admittedly, but it's a very solid result. The problem would mean that we have no gas in falling during that time, but the Milky Way has a bar, and bars are very long-lived. So now we are exploring the possibility that it depends a bit on the field of view, and if the disk grows inside out, and here we actually have been studying more the inner parts of the disk, then this makes a lot of sense. Interesting, though, is this thing. The rough H bin around 1 billion years, we have with relatively narrow bars, something that gives us 5% of the mass, and then something in the last few hundred million years. So what does this mean? So this is not compatible with the quasi-continuous star formation history that has been the standard for 10 or 20 years in the Galactic Center. And we believe that what we see here is not compatible with what has been done before. The star formation history is different in the disk than in the nuclear cluster. And finally, there is this starburst event. So about a giga-year ago, and this is really clearly identified by this double red clump that Paco found. And this is quite impressive, actually. We can also, since the faint signature of the red clump does not survive for a long time, it's a very short-lived feature. So actually this must have happened in a pretty short time scale, being related to something like 100,000 or 200,000 supernovae. So one may speculate that a billion years ago our galaxy looked like M82 for a while. So let's go to star formation now. This is another hot topic, and there's a lot of people studying. Is Johnny Henshaw here? He's not here. So Diederik is here, and well, Melanie doesn't do the Galactic Center, but star formation. So there's lots of star formation people now focused on the Galactic Center. If you just look at, oh, it shouldn't have happened. So if you just look at, this is just a broad offer of images from the Galactic Center in the near infrared. And of course, you see all kinds of things at 8 micrometers. You see a lot of PAH emission. You see optically thick dust clouds, very thick dust clouds. 24 microns, you see some brighter star-forming regions lighting up here. Even SAGB2 already, you see something here. This is the most massive star-forming region in the Milky Way. We know SAGB2 from radio observations because it's so deeply embedded. At 250 micrometers, Herschel, you see lots of dust, lots of cold dust here. This is the famous Mercat one of the famous Mercat images where you see a lot of supernova remnants, for example. And this is a multicolor image between 8 microns, 24 microns, and 20 centimeter radio. So you see there's a lot of activity going on. There's lots of gas, there's lots of cold gas. We see star formation regions. So there's really a lot going on, and that's simply because we're at the bottom of the potential well, and we have, as Mattia can explain very nicely, we have this asymmetric potential because we have the galactic bar, and that drives in gas towards the center. And this settles then down in what is called the central molecular zone, and this contains somewhere between 5, maybe even up to 10% of all the molecular gas of our Milky Way. And this is actually within a very small surface area, 0.1% of the surface area of the Milky Way. So this has nothing to do with the environment of the sun. It's full of stars and it's full of gas. This is a really crowded area. In fact, if you then look at the conditions there a bit more in detail and look at the strength of magnetic fields, turbulence, temperature, the chemistry if you want, the cosmic ray density, you really see that this is a very special region. It has nothing to do with normal disks that form stars, but it's rather like a high redshift star forming region. And this is actually cool because we have a high redshift star forming region right at our doorstep where we can study what's going on. So just to see, this is just a view. Here, this is the velocity longitude diagram where you have the typical parallelogram of what you see in radio regions. This CO emission, actually it's asymmetric, such a star is here, so you have more gas on one side than on the other. So there's lots of gas to form lots of stars, and of course we do see some star formation. So between 2 to 5 million years ago, we have at least 3 very strong star-forming sites. So one is the immediate environment of the black hole, which is actually not a cluster, but rather like a disk. Something like 100, 200 O stars formed there, in total maybe 10 to 15,000 solar masses. And we have the famous quintuplet and arches clusters, which among with Westerlund 1 and 2 are the most massive clusters that we know so far in the Milky Way. Interesting thing is, though, as you see, quintuplet is already less dense than this thing. So give it another, this is maybe 4 to 5 million years old. Give it another 5 million years and you won't see it anymore. It's so dense, the galactic center, that even a 10,000 solar mass cluster just disappears in there. There is also all through the region, that is from a Paschen Alpha survey with the Hubble Space Telescope that was done by Wang et al. And Hui Dong. Hui Dong was also for a while as a postdoc with me. So there's easily more than 100 isolated massive stars throughout the entire region, are scattered throughout this region. So some of them may be runaway stars from the known clusters, but not all of them. That's impossible. And it's not clear which ones are runaways or whether there are any. So we don't know what this is. So they may be associated with smaller clusters that we have not yet found. It also raises the interesting possibility that massive stars may actually form in isolation in the galactic center, which would be relatively unheard of if you go to normal star-forming environments. So what can we say about what's going on here? Okay, this is just the citations. We have at least, I mean, we cannot go too far into the past because then we don't know anymore, we don't have the tracers, but basically we know that over the past 100 million years, on average, we have 0.1 solar masses per year forming there as stars, and that over an area of 0.1% of the Milky Way disk. Compare that with the entire Milky Way, it's like numbers like 1 to 2 solar masses per year for the entire Milky Way. In the past 10 to 20 million years, as a rough number, about 1 million solar masses must have formed in there. We know that from different indicators. From Paco's analysis, or there was a famous paper by Matsunaga et al. In 2011 in Nature about classical Cepheids in the galactic center. Another interesting aspect of all of this is that the galactic center is one of the few sites where we have, let's say, believable evidence that the initial mass function may not be universal and actually be top-heavy currently. We don't know what happened in the past. Or of course, if I want to be more careful, I would say the present-day mass function is top-heavy, because it's always complicated with mass segregation, all of this. So you see high redshift conditions, non-standard initial mass functions, strong star formation. This is beautiful. Lots of supernovae going off. Lots of, well, there should be also, I'm not touching that, but I'll mention that. So lots of supernovae, there would be a lot of pulsars, but actually we hardly know any pulsars in the galactic center. One of the most interesting things that I heard recently is maybe because the magnetic fields are so strong in the galactic center, maybe even the massive stars have frozen in magnetic fields. So, and if you then form the pulsars as magnetars, they will spin down very rapidly and be not visible easily anymore. But this is speculation. It's just to mention. I mean, I'm here to entertain you, so you can go back with interesting ideas in your heads. Now here's another thing. I just say how marvelous this star formation region is, and there's so much going on, but Okay, this is review from Johnny Henshaw, but there's a lot of work also that, so please look at the exact references also in here. If you plot now the dense gas in the Milky Way versus the star formation rate, so green is normal Milky Way clouds. Then you go to other disk galaxies, high redshift galaxies, starburst galaxies, it all is on a nice sequence here. The Milky Way central molecular zone actually is below this. So it's currently, at least the Milky Way central molecular zone seems to be highly underperforming. There's far less star formation going on, at least in the past few million years. So we have to be careful. The timescales are very fast there. We're talking of timescales of at most, where the central molecular zone is, we have like orbital timescales of a few million years. 4, thanks. So at least currently at the very present, something is happening there. I'm not diving in there, but this is another thing that makes it even more interesting, that it's not doing what we expect. Of course, we always love when things do not happen as we expect them to happen. So what open questions do we have about star formation? So of course now one of the important questions is this top-heavy initial mass function, this non-standard initial mass function, really, really true? It requires a lot of nitty-gritty work, because you have to take care of mass segregation, of multiplicity and other problems, hopefully finding some more clusters, get a decently fully survey of what has happened there in terms of star formation in the past 10 or 20 million years. Then, of course, can massive stars form in isolation in the galactic center environment? I think that is very exciting, because that would be something very unusual outside of the galactic center. Another thing is that if you play with molecular gas and star formation and feedback, you want to know where the molecular clouds are along the line of sight. It's not that easy to find that out. Then again, now why is the current, so the present day mass star formation so inefficient at the galactic center? So I'll come to it. You have molecular clouds hanging there that are incredibly massive, incredibly small, and incredibly inert. Why is that going on? And then, of course, as I mentioned, so because of tidal forces and of shock interactions with giant molecular clouds, clusters, even very massive ones, even 10,000 solar mass clusters, they will just disappear within the background population in 5 to 10 million years, rather short time scales. And then you cannot find them anymore, because you cannot use stellar colors easily at the galactic center. Nevertheless, even if I assume I'm very pessimistic and say everything dissolves in 5 million years, there should still a few clusters be hanging around in the galactic center. Where are they? One step forwards is, this is a paper that Paco Nogueras, Nadine Neumeyer, and I did, and it just got accepted in Nature Astronomy. So this is also based on our galactic nucleus data. So there's the Sagittarius B1 region next to Sagittarius B2, of course. And there, using this analysis of luminosity function galactic nucleus data, we find very strong evidence that there must be, there's no obvious cluster, but there's clearly something like 100,000 solar masses in stars, or a few 10,000 solar masses in young stars hanging around there. So this is a very big step into the direction of, okay, we know there's young stars, where are they? Well, a lot of them are there. This is Paco. So, okay, I need to speed up. So I've mentioned now, I've mentioned now everything that we know. So how do we know these things? So let's go to how do we observe this in the infrared? So we have the problem, it's extremely crowded. We have very high extinction in the galactic center. We need to deal with an extremely high dynamic range. So standard imaging runs into problems. This is the VVV survey. So it's a VISTA telescope, the ISO VISTA telescope. If you point, if you integrate, it's just saturated. You have a problem with seeing and everything. This is Hubble, but of course you can't use Hubble all the time and for everything. And this is what we do from the ground with Hawkeye now with my group. So we use a spectral holography technique from the ground, and we can cover very, very large areas, tens of square arc-minute large areas with 0.2, basically with Hubble resolution. And this is really, this has been the key that we've been, it's a key technique that we use, and so this galactic nucleus survey has given us all these tools now to understand the formation history, to discover young stars, etc. And it's just simply because you go from this view, which is kind of the benchmark before our work, we go to this view. This is the current benchmark in galactic nucleus. And just because of the angular resolution, we go at least 100 times deeper because we reduce the crowding by a factor of 10. Still, even if you do the best, this is now ground-based adaptive optics with holography technique, but you still don't really know what you're looking at. What is all this stuff? Is it young? Is it old? So the next step will be proper motions to rescue. Because if you get proper motions, you understand much more, as we all know from Gaia. So for example, if you look at this is a cumulative number of stars versus their relative brightness. So the state of the art is currently here. This is basically what is done with the VVV survey. Because they have been imaging repeatedly the inner galactic nucleus, the bulge, the disk with the VVV, but they run into this crowding and saturation problem in the Galactic Center. And we can go here. So Nuki is the follow-up program of galactic nucleus. This is basically the same thing, but then adding proper motions. We will get we will be sensitive enough to get red clump stars and OB stars that trace recent massive star formation and structure, and we go basically 2 orders of magnitude in numbers and precision proper motions. And then, of course, if you suddenly you can say, okay, this stuff is probably bulge stars, we can take it out, and here we have a co-moving group, and we can analyze it separately, and we have a cluster here. That's the goal. So this is just ground-based AO, and this is ground-based AO with our specular holography technique. So still we can, and this is very good conditions. So we still, even in the K-band, we can reduce still the crowding by a factor of 4 almost. This is also shown here. So this is from a standard ESO program, not ours. Blue, this is astrometric errors in the H-band. Here you run into saturation issues, then you're around here. And with our spectrography technique, we are just at a lower floor of astrometric errors. This is why we can do this work. And actually, we have already combined on just one chip of the Hawkeye camera 2 6 years apart epochs, and we already get down to 0.3 milli-arc-second per year proper motion uncertainty in one axis. The y-axis that is because of the field size, the field shape in the first epoch. So we really hope to get like 0.35 million milli-arc-second per year proper motions for millions of stars as a next step to unlock the galactic center, because if we don't have proper motions, what are we going to do? So this is another work in preparation for this. This is actually using data that have been published by Libralato, at Mattia Libralato, from a WIFC survey, WIFC3 survey, and currently we're looking for co-moving groups in the already published data. And this is with machine learning. You see this is a dense in location. So this is a vector point diagram, so it's perpendicular and parallel to the galactic plane. Very dense group that is also very densely populated here in space. This is X and Y. This is basically just within 7 arc seconds, all these stars. The red dots around is stars that are not co-moving. And if you plot that on a color magnitude diagram, the green dots, they are all have more or less the same reddening, so we also see they're on the same line of sight distance roughly. So this is something we're trying to do at the moment. They have a consistent velocity dispersion. So this is done by my PhD student, Álvaro Martínez, at the moment. Álvaro has also done another work with Álvaro and Paco. There's this brick, I've mentioned it. This is this absolutely fantastic, mind-blowing dense cloud in the galactic center. And then suddenly come along a publication last year that says it's not in the galactic center, it's a kiloparsec in front of the galactic center. And that, of course, would mess up, that would say that all the work that has been done on the brick and all the considerations of how star formation works in a galactic center is invalid. And then we said, wait a minute, and one paper was done photometrically by Paco, and the other paper we do now with proper motions. We have a field on the brick and a comparison field. So on the comparison field, we see what you've seen before. A bulge component, which is broad bulge stars, eastward and westward moving stars of the nuclear stellar disk. If we now go onto the brick, that is infrared dark, it blocks all background light. We only see the bulge component, because bulge stars are everywhere, and the eastward moving stars. And that is, so there's no doubt that this thing is inside the galactic center, inside the nuclear stellar disk, but it blocks the background light. So this is Paco Nogueras and Álvaro Martínez. Okay, I see the first people falling asleep, and I apologize. So I'm talking a bit. So this is really the last considerations now that I do here on going a bit out of my comfort zone, but going a bit out of special consideration. So let's see where's the connection to the central black hole. In the end, we always want to know what happens with the central black hole. All of you are aware of this. This schematic has been around a lot since the last 10 years. So this happened. So we have the Fermi bubbles that were detected by the Fermi satellite, like 10, 15 kiloparsec hot bubbles north and south of the galactic plane. We now see there's an X-ray sheath as well. There's the microwave haze. Then we have there's the radio and X-ray observations also show strong outflows from the center, tens of parsecs. So there's really something going on. And of course, it's always tempting to say it was the black hole. And so there was actually recently a paper in Nature by Yang et al. And they say that maybe 2.5 million years ago, they did a model, the black hole accreted 1,000 solar masses and launched a bipolar jet during 100,000 years, and it all fits perfectly. Which can be true. I just want to discuss that. I personally see it's a complicated matter, and I think this will still take a few years to have clarity on this. So here you see the EHT image, and one of the interesting things is that the accretion disk, according to their models, is seen face on, or almost face on, but it's definitely not inclined, not parallel to the galactic disk. There's actually been, even in Nature, a big article about people being surprised that it is not like this. I didn't get this surprise. It was for me surprising that there was so much surprise, and I think it's basically because everybody has these Fermi bubbles so in their head that everybody just loves the bipolar jets. The gravity collaboration, this is, by the way, scales of micro arc seconds. This is done with the gravity interferometric instrument. They have observed also sometimes hotspots circling, and I've just heard from Frank Eisenhower, they're observing more of these, and they see stuff circling the black hole face on again. So all of this raises a bit the question, how does such a star gain its mass, or how has it gained its mass? So what we currently observe that the accretion flow is not aligned with the galactic plane. And this would mean that if there were a jet perpendicular to it, that doesn't function with the Fermi bubbles. Of course, that can mean that the spin of such a star is not aligned with the galactic axis, so Fermi bubbles are dead. But of course, it can also mean that this fluffy accretion flow that we observe now is not really related to this issue. One has to be careful. I don't understand enough of that, but maybe if you have strong accretion, then something else happens. However, I did my homework and I tried to look it up, and it's really, there's a lot of work that says in spiral galaxies, the jets in AGN can point in any direction. And if anyone can correct me on that, please tell me, but I heard it's random. So it would be strange if just in the Milky Way the thing pointed just in the north-south bipolar direction. So this may be a problem for this jet model, in my opinion. And so some other considerations, really getting to the end now. So we have a 4 million solar mass black hole. This is really wimpy. So I always like to provoke people, not provoke, I always get provoked when people try to say, oh, we love IGN, and therefore let's talk about the Galactic Center. And I say, no, the Galactic Center isn't anything but an AGN. It's no IGN. It's a wimpy black hole. Currently, it's accreting less than 10 to the minus 8 solar masses per year, so you have no chance to build up a black hole with these accretion rates over Hubble time. Tidal disruptions may give you 10 to the minus 4 solar masses per year, and also like every few hundred years there may be short outbursts. We see them as X-ray echoes throughout the Galactic Center, and and they can also accrete a bit, so if you're generous, these 2 points can give you a fraction of the mass of such a star, like 1-2 million solar masses. Also these events, as explained in this jet model, they could also build up such a star, but if you say this has happened 2.6 million years ago, you would expect it to happen relatively frequently. But the problem is, and this I learned, I think mostly from Nadine again, that the stars give you kind of a record of the accretion history. The nuclear stellar cluster is older than 10 billion years, 80% of the mass. So how do you accrete a lot of mass onto the black hole and not onto the cluster? And so this is old. So And this is also 10 billion years ago, is also when we had the last significant merger in the galaxy. So I personally strongly believe, this is a belief, I have the feeling that there's good arguments to see that such a star is a very old black hole. It has formed and it's just hanging around now. This is what I personally believe. The problem, of course, is also the Milky Way bar provides us a solar mass per year into the galactic center. If you accrete that, you would end up with an amazingly massive black hole. Obviously, that stuff is not being accreted. Something must keep the gas from the black hole. It cannot reach such a star. You'd just be immensely massive. So we also know there's a strong star formation going on, and it drives out so 90% of that mass is definitely driven out of the galactic center. So there must be a big wind from the galactic center. Continuously, it's being ejected, this stuff. For example, we also know a million solar masses. We also have lots of supernovae going off. It's true the energy considerations are difficult always with these models. I'm not an expert on that because it depends protons, cosmic rays, or electrons. But you have lots of supernovae going off. You have lots of stellar winds of massive stars. Maybe you form even preferentially massive stars in the galactic center. So you have strong winds. You have a lot of feedback. So to finish, such a star probably acquired much of its mass in the distant past. That is my favorite hypothesis. Star formation may plausibly keep such a star from accreting. Brief bursts of Cepheid activity are probable. There's good evidence for that, but I really think they're of very minor importance for such a star growth. So this is not an AGN. Star formation probably dominates the energetics of the galactic center. Concluding, the galactic center is a wonderful place. And thank you very much for being with me for 60 minutes.
Thank you so much, Rainer, for giving us the benefit of your many years of very careful work and giving us this overview. I certainly thought that was a very comprehensive picture, and I certainly feel that we've heard now the fundamentals of what that data set means. And as you said, there is going to be a lot more to come, especially as one branches out into other spectral ranges. And I'm sure there's going to be lots of questions. We have two audiences. One is here and one is online. And I'll invite first the audience here to ask questions, and then if our audience online could indicate maybe via in the comment either type your questions in or say that you want to ask a question, and then we'll actually attempt to acoustically allow you to give your question. But first, to the audience, are there questions just to kick off, please? Well, there's two. Well, I think, Nadine, you were just beaten to it by about 2 seconds. So I'll just take the microphone to the back. It was actually Didier. I didn't recognize you.
Sorry. Sorry for getting you all the way up here. Brilliant talk, Rainer. So you ended on a rather provocative statement there, which is star formation dominates the energetics of the galactic center.
Yes, I consciously provoked there. I'm at the risk of making a fool out of myself.
No, I think it's a lovely statement, and I couldn't agree more. But I foresee a lot of resistance against that sentiment within the field. So what do you think are the critical observations that would, say, convince the black hole fans to accept such heresy?
Well, by the way, I like to say it because, of course, it's fun to if there were no resistance, it wouldn't be fun to say that. So for me, one of the vital observations has already been done. That's the random orientation of jets in spiral galaxies. So that is already, I mean, we can, yeah, I think that's already a massive argument that is existing. Then I would, okay, I personally would say that we see rather a phase on that, an edge on accretion flow in such a star. And for example, if further observations by the Event Horizon Telescope and also by the gravity group confirm that we see phase on rotation in such a star, I would say that's another pebble stone towards this. Of course, one can always But maybe one can do theoretical models. I think there's this magnetically arrested accretion disk. I throw this name around. I don't understand them. But if those align with the spin of the black hole, then we're done. But I'm afraid one can always do things. I think we can better understand the star formation history and therefore the energetics. We can still work on that one. And as people who are deeply in love or deeply convinced of something, you will never convince them.
Thank you. I'll just pass quickly to Nadine since we're a bit short of time.
Yeah, thank you, Rainer, for this really great overview. I had a question about black hole cusp at the center, because the supermassive black hole is likely also surrounded by stellar remnants. And you mentioned that there was news, and maybe I've missed this. So can you maybe elaborate a little bit more of how we can actually find the cusp of stellar remnants at the Galactic Center? Because also for the visible mass, it was going back and forth whether, there is a cusp or there is no cusp, because we expect it from stellar dynamics, and also the remnants would settle down there, and also they could provide growth, to the mass of the supermassive black hole. So how could we find the stellar remnants?
So first, I think it's Haley et al. 2018, or Generosov et al. 2019. So it's X-ray observations, basically X-ray transients. And because of the recurrence time, I cannot explain that, so I'm out of my turf here. Basically, they claim most of it is probably black hole binaries. So it's really X-ray transients, and there was an old paper from 2005 from Mike Muno, who found more X-ray transients in the central parsec. And now this has been improved by more timescales, longer timescale with Chandra. So there is very good evidence of an overdensity of X-ray transit in the central parsec. And they can actually fit a -2 gamma power law, so a very, very steep cusp. I like that you say, but also you infrared guys, if sometimes the cusp was there, then it was not there, then it was there again. I fully agree with you, because I've been part of that story and partly to blame for this story. We will definitely know, I think, with the event, not the EHT, the ELT, there's just too many acronyms around. The ELT will get us down to solar masses, and then we see really what's going on with the stars. We don't have a crowding problem anymore. And as concerns the black holes, I have the hope, so we have been currently working on the science case of a survey of the Galactic Center with the square kilometer array. And the square kilometer array is going to be significantly more sensitive than what we have now. So I think, for example, if you dedicate each year 100 hours to observe the nuclear star cluster, you will find, over 10 years, you will find many radio transients there as well. And I think that will also provide significantly new information. In the X-ray, unfortunately, we have the problem always of angular resolution, so I think Athena will not help there.
Okay, thank you. So now we'll go across to our virtual audience, and I see that Walter Damon has a question. Let's attempt to do this acoustically, if you'd like to speak, Walter.
It was more a comment than a question. I'm not at all surprised regarding the black hole connection about what you said. And I think I did actually some work theoretically on black hole feeding, and this hole does exactly what we expect, right? It is small feeding events occasionally, and the orientation is random. And of course, the Fermi bubbles must be collimated by the disk. Essentially, the interstellar medium must collimate them. And that also means that they're most likely not driven by the black hole. Or they could well be driven otherwise.
Did everyone understand him? So Walter, I'll try to repeat your words here to the audience. So from his work on black hole accretion, Walter says that yes, there's small random events, a very typical thing. Also the orientation can be fairly random, and that when you have these outflows in Fermis, it's probably the disk itself, the Milky Way disk or the nuclear stellar disk, the gas pressure there and magnetic fields, I guess, that collimate the outflow, so it must not necessarily be from the black hole. Is that correct? Please give me a nod with your head, or did I just... yeah, okay, thanks. Okay.
So we had another question from the Zoom audience. Who was that? I think it was Hans Zimmiker. Yeah, go ahead, Hans. Please unmute yourself.
Hi, Rainer. I'm glad you still like football as much as the Galactic Center. But more seriously, I have a question about the IMF in the Galactic Center. And that refers to these many old stars very close to the black hole. And the problem there is that there's a lot of shear introduced by the tidal forces introduced by the black hole. And this actually causes only very high density clumps to be gravitationally unstable, in which case you, from the Jeans criteria, you would expect to form low mass stars, but the contrary is true. So do you have a theory why this should be so?
Absolutely not. It's good to see you, Hans. No, I have to say that that would be very presumptuous if I comment on these things. I just know that in the central parsec, the massive stars in the central parsec supposedly formed in some kind of disk, accretion disk, and I think the modelers there find that that one forms preferentially massive stars. I think it's Bonnell and Rice is the reference. But I do not want to overstretch my credibilities here by speculating on your questions, because I do not feel qualified. I'm sorry.
Can you repeat?
Are there any more questions from the floor? Okay. Well, I think we can wrap up now. Before thanking Rainer, I'd like to make a couple of announcements. If I can find my... No, it's okay. Yeah. Yeah. Go back here. First of all, next week there will be a change of program, and the colloquium will be given by Thomas Michael Evans, a new group leader at the Max Planck Institute for Astronomy. He's going to tell us about his work on extraplanetary atmospheres. And the second announcement is that we have two meetings where we can discuss further these very interesting questions. First is a student meeting, just a purely private meeting between all the student community in Heidelberg and Rainer, which will take place at Hemingway's, and I'd ask anybody interested in that just to gather at the front here with Rainer after the colloquium. And secondly, at 7:30, everybody's invited to join Rainer for dinner at the Cultural Brewery. So now it just remains for us to thank you very much again for this amazingly interesting and clear and very informative colloquium. Thank you so much, Rainer.
Thank you, Richard. Thank you for inviting me. I always enjoy to be here. Always glad to be here. Thank you very much.